Yo, yo, how's everybody doing? I hope you're doing well. It's weird that I asked that question when you can't really answer it back, but here we are, 15.1, part 1, integer exponents. So we're going to talk about rules and properties of exponents, and then we'll have a part 2, which is going to be a lot more on practice and just talking about the rules a little bit more, because there's a lot of rules here, and it can get confusing. But if you have your rules in front of you, you need to actually look at them when you're doing the problems in the beginning until you get used to it. Because then you won't mix them up, you won't make silly mistakes. Because the math itself is very simple, but it's easy to mix up the rules. So here is all of your rules. You can also look a little bit ahead at 15.1 part 2 notes, and there's a chart with all of this on there. And that chart gives examples. Okay, so we're looking at how to simplify problems with exponents without actually simplifying the exponent. So I'm going to show examples of these on the next slide. And if you want to include those examples in your key terms, you can. So you can kind of go back and forth. Okay. So here we go. So I have my first one right here. So what we have is I have two numbers with exponents. I have 5 squared times 5 to the 5th power. So what we want to do is we're going to simplify this and leave it in an exponential form without actually figuring out what it is when you multiply it. And the reason why is with exponents, these numbers get to be massive. They can be large quick. And it just doesn't make sense sometimes to write such a large number down, so we write it down in exponential form because it's just a lot easier to look at and understand what it's saying. So what we're going to do is we are going to simplify this without solving it. So first, let's talk about what we have. So this is exponential form, meaning I have two numbers in exponents and I have an operation between them. What I could do is I could expand this out into standard form. So what I mean by standard form is 5 to the squared. I'm going to write out what that actually is. That is 5 times 5. It's just 5 times itself twice. 5 to the 5th power is 5 times itself 5 times. I'm going to bring this down right here because now I'm multiplying 5 squared times 5 to the 5th power. So that's 1, 2, 3, 4, 5. So by expanding these out into standard form, like this is just expanding it out so that I can see everything. So I can see all what I'm actually doing. This is a shortcut of writing this. So I have 5 squared, 2 5s, multiplied by 5 to the 5th power. So really what I have is I have 5 times 5 times 5 times 5 times 5 times 5 times 5. I have 1, 2, 3, 4, 5, 6, 7 5s. Which means if I'm multiplying 7 5s by itself, that's really just 5 to the 7th power. Now let's go over that again. So if I have 5 squared and then 5 to the 5th, 5 squared is 5 times 5. 5 to the 5th is 5 times 5, 5 times. Well, if I look at all of this together as one problem, because that's what this is, right? I brought down the multiplication, I just expanded these out, but this is that problem. This, and this are the exact same thing. But I have a total of 7 5s here that are all being multiplied. That is another that is a long way of writing 5 to the 7th power. So 5 squared times 5 to the 5th is really just 5 to the 7th. And I don't need to actually figure out what 5 to the 7th is. We're going to leave it at that because it's a large number that I don't want to know. And so I'm done. 5 squared times 5 to the 5th is 5 to the 7th. This is a product of powers. So this is a product of powers. A product, I'm multiplying two numbers with the same base. They both have a base of 5. And I'm adding their powers together. So whenever we have the same base, like that, that should be, I'm sorry, I put a plus sign there. That should be a multiplication sign. So whenever we're multiplying two numbers with the same base, all we're doing is we're just adding their exponents. And I I even wrote the answer here, so it should have been a 5. So that's equals to 5 to the 7th power. That's really all we're doing. You don't have to expand it out every time, but when in doubt, you could always expand it to see what's happening. Okay. So let's look at, this would be a quotient of powers. The reason why it's a quotient is because it's dividing two numbers with the same base. So now let's look, if I were to expand this out, 6 to the 8th, that means I have 8 6s on the top. Or that's 5, 6, 7. I have to do it. It's okay, we'll just go over it. So that's 8 6s on the top, and this is 3 on the bottom. So that's really what I just expanded it out. This is my expanded form where I have 8 6s on top because this is 6 to the 8th power. So 6 times itself 8 times. I have 3 6s on the bottom because 6 to the 3rd power is 6 times itself 3 times. So if we look here, 6 over 6 is 1. That cancels. 6 over 6 is 1. That cancels. 6 over 6 is 1. I'm left with 1, 2, 3, 4, 5. So that's 6 to the 5th power. So by expanding it out, I saw that 6 to the 8th on top, 6 to the 3rd on the bottom. I know that 6 over 6 is 1 and cancels out. We've learned that property before. So by doing that, I'm out of 6s on the bottom, but I still have 6 to the 5th on the top. So therefore my answer is 6 to the 5th. And again, this is quotient of powers, where if I have something like 6 to the 8th over 6 to the 3rd, that's really just equal to, if I have the same base, we're just subtracting the top from the bottom. And it's just a subtraction problem. That's 6 to the 5th. So when we're multiplying two numbers with the same base, we just add the exponents. When we're dividing two numbers with the same base, we're just subtracting the exponents. So this is where I was saying that the math itself is actually pretty simple. Because you're just, all we did here is 2 plus 5. All I did here is a minus 3. But it's mixing up these rules, knowing when to add and when to subtract is when people get in trouble. All right, I'm going to erase these. Now we can look at the next one. Here I have 7 squared, all raised to the 4th power. So again, I'm always going to expand it out to show you what's happening here. So let's expand this. So this is a power being raised to another power. So if I have 7 squared, we know that that is 7 times 7. So all I did is I expanded out 7 times 7. 7 squared is 7 times 7, which is what we know. I'm going to leave my base. I'm not actually going to multiply that and make it 49 right now. All of this is being raised to the 4th power. So if all of this is being raised to the 4th power, I have this piece right here 4 different times being multiplied by itself 4 times. So let's expand that out. So that's 1, 2, 3, 4. Because what I did is I took my 7 times 7, that's 7 squared, and I have 4 of those. That's being multiplied by itself 4 times. So I multiplied it by itself 4 times. Well, now I have a total of 7. 1, 2, 3, 4, 5, 6, 7. I have a total of 8 7s. And they're all being multiplied. There's nothing in between this. This is just multiplication, right? It's all just multiplication. So because all this is being multiplied, I can write it as 7 to the 8th because that's just 7 times itself 8 times. So that's 7 to the 8th power. This is a power of a power. This is a power raised to another power. If I have 7 squared, that means I have to multiply. This is probably the most common mistake is people still want to add this. But if I have a power being raised to another power, it's when I just multiply my 2 exponents. 2 times 4 is 8, which is what we got when we expanded it out. Finally, good old negative exponents. Negative exponents, they look weird, right? Like, what? You can have a negative exponent? What does that mean? What that means is whenever we have a negative exponent, we have to flip around it as a fraction. So here's what I mean by that. That sounds really confusing. That's a terrible explanation, but let me show you what I mean. Anything, we can write anything as a fraction. I can put all of this over 1, right? 5 over 1 is 5 squared over 1 is still 5 squared. 5 to the 5th power over 1 is still 5 to the 5th power. So I can still put this over 1. Whenever we have a negative exponent, we have to bring that exponent and its base and flip it If it's in the numerator, we got to take it to the denominator of a fraction. If it's in the denominator, we got to take it to the numerator. So we just flip it and make it positive. Because we don't like negative exponents. Negative exponents, we don't know how to evaluate those. And so we don't use negative exponents, we make them positive. But the way we make them positive is we flip the fraction. So here's what I mean. Because this is over 1, I got to bring this to the bottom, so I'm going to move the 1 over to the top. We're going to flip this whole thing and just make it 1 over 6, and now it's a positive exponent square. And that's it. We don't have to do anything else. When you move it from the top to the bottom, it now becomes positive. I know that one's weird. That one takes some practicing to see. That's the rule. I can show you other examples. Let me show you over here another reason why. Let's say I had these flipped. So let's say this might give it a better explanation as to why we do this. Let's say this is 6 to the 3rd over 6 to the 8. So we said that if I expand this out, I'm going to have 6 times 6 times 6 on the top, and then on the bottom I'm going to have 8 of these, right? We know that we subtract them. 5, 6, 7, 8. We know that these cancel. Look what's left here. I have nothing on the top. When I have nothing on the top, I can just throw a 1 out there. But how many do I have left on the bottom? I have 5. So this becomes 1 over 6 to the 5th when I expand it out. Now let's take this step to show how we did it with our properties. 6 to the 3rd over 6 to the 8 is just 6 to the 3rd minus 8. Remember, we just subtract the top and the bottom. Well, 3 minus 8 is negative 5. So when I use my quotient of powers, I get, for this problem here, I got negative 5. Well, when I expand it out, I get 1 over 6 to the 5th. So these are equivalent to the same thing. But we don't like negative exponent answers, so whenever we get a negative exponent, we do have to make it positive by flipping it. Okay. We're going to move a little bit quicker through these last ones, because those are the main properties. Okay, those are the main properties. Okay, so let's look at this one. So this one right here is power of a product property. So we can kind of look at this one. I like to look at it like distributive property. So if I have a bunch of stuff being multiplied in here and I'm all being raised up by a power, what we're doing is we're just distributing this power to each piece. So really this is 5 to the 3rd power times 6 to the 3rd power. I can just leave it there. I'm done. Or I can figure out 5 to the 3rd and I can figure out 6 to the 3rd, and then I can multiply those two numbers. But it's just distributing this 3rd power to both pieces on the inside of the parentheses. Now, for this one, it's very, very similar. Okay. So, oh, sorry, I got a visitor. 1 second. Okay, sorry about that. Okay, so this one is there's about, it's similar to the last one, but there you could distribute it. There's a lot of ways to look at this. So first we have a negative exponent. Also, I have a quotient, I have a fraction inside. We can just treat the fraction as if it's a regular number if we want. And I'll show you what that means. Or we could even use it where we distribute this to both pieces inside of there. It doesn't actually really matter. So here's what I mean by that. Let's just treat this fraction as its own number, so we're not going to do any distributive. And let's just say I'm taking this 2/3 and I'm raising a whole 2/3 all to the negative 3rd power. Well, we're going to follow our rules with negative exponents. When we do negative exponents, we flip the fraction. So it's going to become 3 over 2, all raised to the positive 3rd power. Now, because what I did is I flipped my fraction, just like what we did over here, right? Flipped it. So that 2/3 is all being raised to the, I'm sorry, that 2/3 to the negative 3 is really 3 over 2 to the positive 3. Now, what we can do is I get to show what this is really happening here. This is really 3 halves times 3 halves times 3 halves. Because I just expanded this out. Well, this is 3 times 3 times 3, which is 3 to the 3rd power over 2 times 2 times 2, which is 2 to the 3rd power. So we are just using distributive property. This is really 3 to the third and 2 to the third. This is one where we could actually solve it, because that would be 27. 3 to the third power is 3 times 3 times 3, which is 27. 2 to the third power is 8. So the answer is 27 over 8. Or 3 to the third over 2 to the third would be just fine. Okay, finally with variables, it doesn't change the process. So I have the same variable 3 times here. So I'm multiplying this 3 times. I have b times b times b. But I have b to the 4th, b to the 7th, b to the 1st power. If there's not an exponent there, it's just a 1. Well, this is all being multiplied, so it's similar to this one. I have the same base. They're all the same variable. So 4. So this is really b to the 4th plus 7 plus 1, because that's how many total b's I have. I have 4, 7, and 1, which gives me b to the 12th power. I'm multiplying them, so I can just do my product of powers property. This is 4 b's, this is 7 b's being multiplied, this is 1 b being multiplied. I have a total of 12 b's being multiplied. Okay. Now this is where we have to combine all of our properties and what we just talked about into multiple steps. So for this one, I have 9 times a to the 13th power over a to the 3rd. The 9 just gets to kind of stay there. If I had another number down here, I would then simplify the whole numbers and just leave the whole numbers with the whole numbers and then worry about the exponents with the exponents. So the 9 just stays there because there's nothing to simplify the 9 with. And now I get to deal with a to the 13th over a to the 3rd as if it's its own thing. Well, this is a quotient of powers. 13 minus 3 is 10. So that's just 9a to the 10th. And I'm done. It's very similar to combining like terms, where we deal with the similar bases, get to deal with each other with their exponents, whole numbers deal with each other, those are like terms, and that's it. So I'll show you what I mean by that like terms thing right here. We'll get more into that. So here I have 2 variables. I have k and I have x. I cannot do anything with k and x because they do not have the same base. They are different variables. So therefore, hold on. Sorry. So therefore, I cannot combine them, I cannot multiply them, I cannot add these exponents because k and x's are not the same. So what we do is we combine like terms. So I worry about 15 over negative 3. I'm going to simplify that as if it's its own problem. 15 over negative 3 is negative 5. So I got that part done. Whoa, I just filled that on accident. My bad. Okay. So now, let's look at the k's. So if I had k to the 7th over k to the 5th, just those. If I'm looking at just these with nothing else, k to the 7th over k to the 5th. Well, 7 minus 5 is 2. So that would be k squared. And this x to the 3rd still stays up here because nothing happens with it. So I'm done. That's my final answer. I'm multiplying negative 5 times k squared times x to the 3rd. I cannot combine k squared and x to the 3rd because they don't have the same base. I simplify by doing my subtraction. And I simplify by doing 15 over negative 3 is negative 5. And there's nothing else to do here. And then finally, this all works similar over here, even when I'm being multiplied. So when I'm multiplying, I multiply my whole numbers. 6 times negative 3, negative 18. X squared times x to the 5th. So I need to do x squared times x to the 5th. Well, I'm just multiplying 2 numbers, 2 of the same base. So I have 2 x's, I have 5 x's. That gives me a total of 7 x's. And I'm done. So now what we do is when we have problems like this, we just take the properties that we learned and we can do it with like terms, really like bases. Okay, I know that was a lot. Okay, things to remember. Practice is important. Yes, please write that down. Because that's really the big thing to remember. There's too much other stuff to write down. Things to remember is that practice with these is super important. Make sure to ask questions if you need help. Here's your independent practice. Hope this helped. Thanks for watching, guys. Grudius out.